Okay, hello and welcome back everybody. So we're on the worked examples for vectors, vector spaces, linear combinations, dependence, and independence. And that's quite the title. But I want to start off by doing a very quick review of what we've actually covered in the course so far, because this is actually a really good section to get into synthesizing everything we've covered so far. So let's recall that so far we've learned about sets, which were important to define vectors, vector spaces, etc. We've learned about maps and functions, which so far have been important since they are vectors, but in fact this will come in to become more important later. It'll be more important for other reasons later. We've learned about indexing, which was very important to condensed notation for, a set that may be large. We're allowed to condense our notation quite a bit. We've learned about sequences, which are basically just indexed sets with an ordering. And in fact, vectors will be these. Basically, every vector is a sequence. We've learned about summations, which is a sum over all elements in a sequence, which we'll find is important for a few reasons. This is definitely important in vector spaces, since by definition vector spaces contain linear combinations, and linear combinations are summations. Maybe I'll mention that here. Linear combinations are summations. And finally, we've learned about the complex numbers and the algebra of complex numbers. And this is very important in quantum mechanics, since Schrödinger equation bakes the imaginary number right into it. And basically where we're headed is that, quantum mechanics, let's call it QM, exists in a complex vector space. So this is where kind of everything came together. So a lot of these earlier ideas, sets, maps, functions, indexing, sequences, summations, they're all kind of sitting around to construct the vector space for me, and the complex numbers are there so that we actually know how to use this particular complex vector space. That's really everything we've covered so far. And so complex vector spaces, along with the Schrödinger equation, kind of the same thing, complex vector spaces should be the primary object of study for most of the rest of the semester. So from now on, you should really only be thinking about complex vector spaces. Now with that said, I will resort to real vector spaces periodically, just because computations get easier. And so, put in parentheses, we may use real vector spaces to gain intuition and make computations easier. But really our primary studying point of this semester is the complex vector space. So real vector spaces will show up basically the whole time, but we want to be able to apply everything we learn about the real vector spaces to complex vector spaces as well. So let's actually get into these worked examples for vector spaces, etc. And I'm going to start with, let's recall the definition of a vector space. So V, a vector space, is defined by a sum, C1, V1, where I use this over vector notation. to denote vectors. And keep in mind, since functions can be vectors every so often, those may be functions as well, but I'll still use that over vector notation. And then the c's, since they don't have the over vector on them, those are scalars. Those are either the real or complex numbers. So a vector space looks like this, where let's say each c1, c2, cn, and now let's give ourselves a complex vector space. This could be R as well, either one. And v1, v2, vn are vectors. And we just recall that vectors is any object that can be scaled and added together. So as long as we have some notion of scaling and adding together. This is a vector space, and in fact, this is actually the definition of a finite dimensional vector space. One could imagine if I took the sum over infinitely many terms instead of finitely many terms, which we learned how to do in our summation section, then we could have an infinite dimensional vector space. We'll get into the definition of dimensional in a future video. It's not too far away, but let's just think about these sorts of vector spaces for today. And we can condense this notation considerably under our notions of summation. And by that, what I mean is that this term here, that's really defining the vector space for us, that is a linear combination of a bunch of vectors, that is a summation. So since the linear combination is a summation, we can actually get away with some better constructions of V. Let's construct V as, using some Einstein summation notation, C superscript k V subscript k. And now we can just say that Ck for k equals 1 to n is a sequence in C, and V sub k equals 1 to n, is a sequence of vectors. And so because of Einstein summation, we can get away with that. Recall Einstein summation, since the superscript and the subscript are the same letter and they're indexed over the same set, going from 1 to n, then we can actually interpret this Einstein summation as Ck v vector k equals, well, we also have the sigma notation here. Let's say k goes from 1 to n of Ck v sub k, which is also C1, now I'm using a superscript, v1 plus C2 v2 plus ... plus Cn Vn. And so we have, because of Einstein summation, a nice little shorter way of writing a vector space. This is useful as we can consider any element of V, this capital V vector space, as taking the form C to the k V sub k. Keep in mind this is always an index, that is not a power. So it's just an index, but we put it in the superscript so that we can use Einstein summation. So this gives us a really nice shorthand. Nice shorthand for arbitrary vectors of V, or arbitrary elements of the vector space. There's also one name given to the set V coming from a collection of vectors. If this is my sequence of vectors, this name is called the span. Okay, we denote it by, so we'll say capital V equals the span of this set of vectors, which happens to be the same as what I've already been showing. I won't use Einstein summation here, I'll use the regular sigma notation, C, K, V, K, such that ck in C and vk vectors. So this is a good word to keep in mind, span. We're going to be seeing it all the time, especially today, but also in the future. So that's one extra nice word that we can think about. And now we have better notions of linear dependence and independence. We can now say that vk plus, or n plus 1, so some vector, is linearly dependent of a collection of other vectors if vn plus 1 is an element of or inside of a span. We're really condensing our notation quite a bit here, which is very useful. So that's a definition of linear dependence. We can now say that vn plus 1, a new vector, is linearly independent of a set of vectors if vn plus 1 is not in. So when I put the slash through, means not in. So now I'll say I'm not in the span vk, k equals 1 to n. So that gives us a nice modification on linear dependence and independence. Let's actually get into some examples. So what are my examples going to be today? Our examples are all going to be focused on determining dependence or independence. In some sense, as long as we're really confident about determining dependence and independence, everything else that we've talked about between constructing vector spaces and Einstein summation, etc., everything else should come for free, our understanding of everything else. Now I'm going to give myself some leeway with these two words since I write them all the time. If you see me write LD, that's linearly dependent. If you see me write LI, that's linearly independent. So that's just going to help me condense what I'm writing about the rest of today. So let's start with our first example, and we'll work with a real vector space here. So let's keep in mind the real vector space R2 can be defined by A10 plus B01 such that A and B are elements of R and 1001 are vectors. Keep in mind this is equivalently the space A, B, such that A, B are in R. So that is a common vector space. Let's look at a couple vectors in R2 and determine if we are linearly dependent or independent. So is the vector root 2, negative root 2, linearly dependent to the set 3, 1, 1, 1. So we always have to compare, every time we have this question about dependence or independence, it's always as compared to another set. And the way we check is we just go back up to our definition. So we look at this definition, we have to check if we are sitting inside of the span of that set. And what is the span of a set? The span of a set is just all linear combinations of elements in that set, or the sum of all vectors in that set with arbitrary coefficients. Okay, so if we're going to do that here, we need to check root 2, negative root 2, is that inside of, so I'm going to write the question mark over the existence symbol. So is that inside of the span of this set, 3, 1, 1, 1? And what does the span look like? Well, it looks like all possible linear combinations. So A, 3, 1 plus B, 1, 1. Sum A, B, and R. So we basically just ask, is there a choice for A and B and R which yields root 2, negative root 2, equals A, 3, 1 plus B, 1, 1. That's the question we have to answer yes or no to. If we can answer yes, then we gain linear dependence. If we answer no, we gain linear independence. Now, what's the easiest way to check this? The easiest way to check this is to write a system of equations by looking at each row in the equality. By that I mean there's a row up top, and here's a row on the bottom. We're going to look at both of those rows. Now you may be wondering what happens to A and B there. A and B are allowed to distribute to each element inside of the vectors here. So we'll distribute A and B, and then we'll look at each row individually. So if I do that, my system of equations, what is my top row? My top row is root 2, this top row. Root 2 equals 3 times A plus 1 times B. And my bottom row is negative root 2 equals 1 times A plus 1 times B. And now we just have to ask ourselves the question, does this have a solution? So let's check and see if this has a solution. So the easiest way to do this, just like a previous video, is to do the substitution method. Let's solve for B. Get root 2 minus 3A equals B. Now that I know that, I can use that B and plug it in to the second equation. So plug in B. And when I plug in B, I end up with negative root 2 equals A plus root 2 minus 3A. If I simplify everything, what do I have sitting around? I can subtract root 2 from both sides, and I can combine my terms that all have a's on them. What that gives me is negative 2 root 2. I have 2 copies of a negative root 2 on the left, and 1a minus 3a's is negative 2a. So it's pretty quick to see that a, after dividing both sides by negative 2, cancel, 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 a is root 2. Once I know that a is root 2, I can plug it in my equation for b, and I recover that root 2 minus 3 root 2 equals b, or rather, root 2 minus 3 root 2 is negative 2 root 2 equals b. And so I've found a collection of a b as well as an a, which give me the ability to reconstruct my original vector. So what have I found? I found that this original vector, root 2, negative root 2, is equal to a times 3, 1. But what was a? A was root 2. So it's equal to a root 2 times 3, 1, plus b, which was negative 2 root 2, times my second vector, 1, 1. And so the fact that I can write the first vector as a linear combination of the other two means that we verified linear dependence. So in other words, the original question, is the vector linearly dependent to the set? Yes, that is our answer. So that's really all there is to it. We can basically continue this idea as much as we want, and we will. A couple more examples today, just so that everybody gets a good idea of what it means to be independent or dependent to a set. So let's look at an example with the complex numbers here. Let's go with C3 and make our lives fairly difficult. So with C3, I have one value against 1, 0, 0, plus another coefficient against 0, 1, 0, plus another coefficient against 0, 0, 1, such that those three coefficients are all elements of the complex numbers. Or in other words, what does my vector look like? C1, C2, C3, such that C1, C2, C3 are all in capital C. I'll ask the question, is the three-dimensional vector 1, I, 0 linearly dependent to the set 1, 1, 0, 0, 0, 1? So our question should basically be the same. We need to check, same as before, does 1, I, 0 equal some constant times 1, 1, 0 plus another constant times 0, 0, 1? And the way we're going to do this is just as before. We're going to read everything horizontally. That's one equation. That's another equation. And this is a third equation. And we're just going to try to solve it for our unknowns. So my system of equations becomes 1 equals, now keep in mind that this C1 here distributes to every term, and the C2 distributes to every term. So we have in the top row, 1 equals C1 times 1 plus C2 times 0. My middle row gives me I equals C1 times 1 plus C2 times 0, and my bottom row gives me 0 equals C1 times 0 plus C2 times 1. And so I recover fairly quickly. If I solve this, this row tells me that C1 is equal to 1. This row tells me that C1 is equal to I, and the bottom row tells me that C2 is equal to 0. I immediately recover a contradiction. Notice that C1 is required to satisfy C1 equals 1 and C1 equals I at the same time. Since 1 is not equal to I, so I've been told, we cannot form 1I 0 from a linear combination of 1 1 0 and 0 0 1. Well, if you can't form it, if you can't form the linear combination, then the answer is no, we are not linearly dependent. In fact, we are linearly independent. So that is a nice way of checking in a complex situation. That one was perhaps a little too easy, so let's consider kind of a modified version of the above. Let's modify the above by asking, is the vector 1i 0 linearly dependent to the set of vectors 1 1 0 0 0 1. So these were the same two as before. But let's add another vector here, 0 1 1. So let's add the vector 0 1 1 into the mix and see whether or not that changes anything. Well, now what do I have? Now I have the following that I need to check. Need to check if 1i 0 equals C1 1 1 0 plus C2 0 0 1 plus C3 0 1 1 for some collection of C1, C2, C3. And just like before, we just read across horizontally. So there's my first equation, my second equation, and my third equation. And if I write out my system of three equations, the first equation is 1 equals, well, C1 distributes to every term, C2 distributes to every term, and C3 distributes to every term. My first equation is 1 equals 1 times C1 plus 0 times C2 plus 0 times C3. My middle equation is I equals 1 times C1 plus 0 times C2 plus 1 times C3. So the fact that I've added another term to the second equation is kind of what's going to save me in this situation. The third equation reads 0 equals 0 times C1 plus 1 times C2 plus 1 times C3. As always, we'll use the substitution method, and the first makes my life really easy. To solve for C1, it just tells me that C1 is equal to 1 from the beginning, and then I can use that in the second equation and plug in C1. I could try to use it in the third equation, but you'll notice that there is no C1 there, so it doesn't really need to occur. But if I plug in C1 in the second equation, I recover I equals C1, but I'm plugging in a 1 instead. I equals 1 plus C3. Now the substitution method is going to allow me to solve this for C3. Right? There's only a C3 there, so I can certainly solve it for C3, subtract 1 to the left, and I recover I minus 1 for C3. And then I can use this value of C3 into the final equation and plug in C3 to recover that 0 is equal to 0 plus C2 plus the new value for C3, which was I minus 1, and I can solve for C2. I'm just bringing the I minus 1 to the left-hand side to recover that C2 is 1 minus I. So what I've established is three constants which allow me to construct my original vector from the other three. So I can say that hence my original vector 1i 0 is equal to, well, it's one copy because C1 was 1, so it's one copy of 1 1 1 or 110, plus C2. C2 was chosen to be 1 minus I. 1 minus I copies of 0, 0, 1. And finally, C3, which was I minus 1. I minus 1 copies of 0, 1, 1. So the fact that I'm able to construct this linear combination of the three to give me the fourth I'm looking for tells me that I am linearly dependent. Yes. So basically what we're learning is that every time we try to solve this system of equations, if it has a solution, I can answer yes. Every time the system of equations has a solution, I can answer yes to my answer. But in case every so often the system won't have a solution, and that's when you can say no. You can say yes or no, depending. Now I do want to finish off with a little bit more tricky of an example. We're going to recall that some vector spaces use functions as vectors. So let's recall this space, P2, the two-dimensional or the second degree polynomial. So this space looks like a x squared plus bx plus c, such that a, b, and c are in R, and x squared, x, and 1 are vectors. So this is a nice vector space that is not going to necessarily look like just the column vectors or the parenthesis vectors that you're used to. We can ask the same sort of question. So we can ask, is the vector, now I'm going to write down a vector here. So is x squared plus 2x plus 1, so that is a vector, a valid vector, just not of the form given as a column, right? Perfectly valid vector. Is that linearly dependent to the set of vectors x squared plus 1, 2x minus 3, and x. So now we're asking a question, is this one polynomial over here dependent to a collection of 3 different polynomials given there? And we're going to answer this question the same way, we just maybe don't have access to reading things horizontally. We have to get a little bit clever about what it would mean to read horizontally in this case. So the definition of linear dependence is the same. We need to check if the vector we care about, x squared plus 2x plus 1, is equal to a linear combination of the vectors we're checking against. So this would be something like c1 x squared plus 1, so that's the first entry. So maybe we say c1, c2, c3. We're going to scale multiply each of those, plus c2 times the second one, 2x minus 3, plus c3 times the third, x. So we need to check if this is true for some c1, c2, or c3. Now it's going to be to my advantage to expand this. Let's expand and rearrange as something x squared plus something x plus something, because then I can compare, you could compare these entries here, 1, 2, 3, to the left. Because over here I've got a 1, and then a 2, and then a 1. So I can compare those 3 to what's on the left-hand side. So let's go ahead and do that and expand and rearrange the right-hand side. So I've got a c1 x squared, I'm just distributing everything. c1 x squared plus c1 plus 2c2 x minus 3c2 plus c3x. And now let's combine like terms. So my like terms, there's an x squared. I only have one of them. So I've got c1 x squared. And then my like terms that have an x on them, I have a 2c2 and a c3. And then my like terms without any x's on them, I have a positive c1 minus 3c2. This is to my advantage because, like I said, I can take this 1, which is the term against the x squared, and I can compare it to c1. I can take this 2, which is the term against x, and I can compare it to 2x2 plus c3. And I can compare the 1, which is the term all by itself, I can compare it to the term all by itself. So that's where I'm going to extract my system of 3 equations from now. This is what it means to read row by row. My system of 3 equations, the first one comes from the x squared terms. I have 1 equals c1. My second one comes from the terms with an x. I have that 2 equals 2c2 plus c3. And my third comes from the individual terms. Without an x, I have that 1 is equal to c1 minus 3c2. It's nice enough that the first one I can pretend like I'm solving for C1, but it's already there. So I have that C1 equals 1. If I'm using substitution method, my second row doesn't have any C1s in it, but the third row sure does. So I can plug in C1. And I end up with 1 equals 1 minus 3C2. Or if I solve this for C2, I subtract 1 from both sides, I find out that negative 3C2 is 0, also known as C2 is 0. And in the last setting then, I can grab C2, plug it in here, and I just found out that it's 0. Plug in C2, I found out it's 0, I end up with 2 equals 2 times 0 plus C3, so we end up with C3 equals 2. Now I've found 3 coefficients for which I can state kind of the linear combination idea, where if I take each of my original vectors, which was x squared plus 1, 2x minus 3, and x, and I attach the specific coefficients to these 3 vectors, the coefficients of 1, 0, and 2, then what I should end up with is what I wanted to. Let's just verify this really quick. If I multiply x squared plus 1 by 1, I get x squared plus 1, the next one by 0, and the next one by 2. What am I left with? I'm left with x squared plus 2x plus 1, which is what I wanted to recover. So that means I found a collection of 3 coefficients for which my one polynomial is equal to a sum of the others. As long as I can find those coefficients, the answer to linear dependence is yes. Anyway, that's all I've got for you today. It was a bit longer, but also a very interesting lesson, so I hope you liked it. I'll see you in the next one. Bye.